In this video, I'll be talking about resultant vector. As we know, vector are quantity that have both magnitude and direction, and as such, the magnitude and the direction plays an important role in the result that we get. Now, when we have more than one vector acting in the system, we tend to consider the net action of all of these vectors. And so therefore, we talk about the resultant vector or the resultant. Now, what is the resultant vector? Resultant vector is simply a single vector. It's a single vector actually that has the same effect both in magnitude and direction as every other vectors acting at a particular point or on a given body. So what does that imply? If I have, like, say, vector, this is a vector, another vector, another vector, and another vector. These are like four vectors acting at this same point. Now, there is a net action. Let's say on this point, they are able to cause this point to move in this direction. Then, what this their action is the resulting action. And this resulting action is caused by the resultant vector. So, in this particular lecture today, we want to talk about how to find resultant vector for different cases. So let me start with the first one. The first case, I'll call it case 1. Now, the first case, which is case 1, is the case whereby you have two objects and two vectors acting in the same direction. So let's say we have two vectors, v1 and v2, acting in the same direction. Now, what do we mean by this? If these two objects, they are acting in the same direction, that is, both orientation are the same, and I'm going to draw something like this here now. So let's say we have, from this point, we have vector v1 going in this manner. This is vector v1, and I have vector v2 going in the same direction as well. This is vector v2 down here. Now, they don't necessarily have to be of the same magnitude. Then, both of them will be acting on this point in this way. Then, the resultant vector in this case is just for us to add v1 and v2 together. I mean, their magnitude. Of course, their direction will be that same direction that both of them are moving towards. So, this is the magnitude, and the direction will be the same direction that both of them are moving towards. Let's look at the case 2 now. For the case 2, we'll be looking at these two vectors. They are moving in opposite direction. So v1 and v2 in opposite direction. So, and this opposite direction is directly opposite. So what do I mean by that? If this is the point and we have vector v1 acting in this direction and we have vector v2 acting in this direction. So as you can see, if we have this to be v1 and we have this to be v2. So the resultant vector, as far as the magnitude is concerned, will be v1 minus v2. Now, if v1 is the greater one, then the direction of the resultant vector will be in the direction of v1. If v2 is the greater one, then the direction of the resultant vector will be in the direction of vector v2. And that is that about them moving in the opposite direction directly to each other. Now, let's quickly go to the third case. The third case is when these two vectors are acting perpendicularly to each other. When they are acting perpendicularly to each other. That is, meaning of perpendicular is that they are at angle 90 degrees to each other. Now, let's call this vector v1 and let's call this vector v2. One thing you will notice is that their resultant must actually come from in between them like this. Their resultant cannot go in any other way than a path that the two of them have created for the resultant force. You cannot find the resultant force going in anywhere in this side, not at all. So the resultant force can only fall from this range to this range. So that's where the resultant force is. So let's assume that our resultant force is here. Now here, I will use the parallelogram law of resolving forces. And what does that tell us is that as this is a vector, actually, you can actually draw a similar vector that is parallel to it as well in this direction. Now, this vector will also be v1. So that is so that it does not really matter where the vector v1 is, as long as it is parallel and it is of the same, magnitude, it is still the same vector. It's just changing direction. So now we have a new diagram. Now this is like a right angle triangle, and here we have v1, and here we have v2. Still, this is 90 degrees, and this is the resultant vector. Here now we use the Pythagoras theorem. That means that the magnitude of the resultant is v1 squared plus v2 squared. Now, if we are asked the direction in this place has to do with angle, and let's say this is angle theta, and this angle theta is made with the horizontal, or we can say made with vector v2, the horizontal vector. Then the direction in that sense is given as the arctan of v1 over v2, where what theta is the angle made with the horizontal, or the angle made with the horizontal vector. You can also find this the direction in this manner. Let's call this one alpha. Of course, we know that sum of alpha and theta would be 90 degrees. Sum of angles in the triangle is 180, and this is already 90, remaining 90. So which implies that if this is the angle you are looking for, then your alpha will be 90 degrees minus theta. But oftentimes, this is the angle that you would always use for your direction. Now, the fourth case is the case whereby you would have to use the triangle law of resolving forces and even the parallelogram law. Now, let's say you have two vectors. Let's say this is vector v1, and you have another vector. Let's say this is vector v2. They are acting in this direction, and then there's an angle theta between them. You don't know what this theta is. Of course, like I've said, their resultant will always come in between them. So let the resultant come like this. Now, the first thing I want you to take note is that this resultant does not cut this angle into equal halves. So this side might be greater than this side, and this side might be greater than this side. So we don't know that one yet. Now, here's what we do. Just like we did earlier, we draw a parallel vector rather to v1. So let me draw a parallel vector to v1. So I'm going to draw it here. It's meeting up with this. So this is v1 right here. Of course, we can draw a parallel vector to v2 as well, but I don't need that in this case. Now, with this now, I have v1 on this side. Then I have v2 down here. The next thing is that I want to get the angle that is in this place, but I'm not sure what the angle is going to be. Now, here's what I'm going to do. I'm going to extend this. If I extend this, one thing we know is that according to mathematics, we have something that is called corresponding angle. If from this entire thing, angle v1 and vector v1 is making angle theta with this, and since this v1 and this v1, they are parallel to each other, according to that law of corresponding angles, if you have two parallel lines and you have a transverse line, the angle here, if it is theta, then the angle outside there will be theta as well. Therefore, angle on a straight line is 180 degrees. That implies that the angle inside here would be 180 minus theta, because the angle on one end is theta. Now, from this place now, I can bring this out. So I have a triangle that looks like this. Now, this triangle right here, it is not a right angle triangle, by the way. So it is not a right angle triangle. Yeah. So, and it could be a right angle triangle, but I just wanted to ignore that fact. So V2 is going this way. Then V1 is going in this direction. Then inside there we have 180 minus theta, and this is the resultant force. Here is where we use the cosine rule. To use the cosine rule, we're looking for r. So here we know that r squared equals v1 squared plus v2 squared minus 2v1 v2 cosine of 180 minus theta. Now, you can continue to use it this way, or you can use trigonometry, and this will be v1 squared plus v2 squared. Now, cos of 180 minus theta is actually the same thing as negative cos theta. Negative cos theta. So, when you do that, you have a negative sign here and you have a negative sign here. It becomes positive. So, you have plus 2v1, v2, then cosine theta. Anyone you decide to use there, they would work perfectly fine. They would work perfectly fine. So let us proceed now. If you then have, now this is the fourth case. Now there is the fifth case, which I will discuss in the next video. So if you want to see more videos like this, don't forget to subscribe and follow. I'll see you in the next one.